You have just heard here that research over 50 years, and we are very much proud of that fact that for the elementary Indian mathematics, and that he is going to present here. That so by being an Indian, we must be very proud of that. And also I am proud to be the presence of Professor Parthasarathi Mukherjee here. He is my Guru Bhai and also my friend very well, and he is also doing very good deep research on the Indian history of mathematics. So I hope that, and also I am thankful to Amartada and to organize everything. And so I hope the lecture will be very enjoying, and we will learn something from the lecture. Thank you. So please, Professor.
Thank you. Thank you. Well, this day was a long time coming for me. I'll just explain why I say that I started thinking about Indian mathematics 50 years ago. I didn't know that what I was thinking about was the lost logic of elementary mathematics. But that was my experience in class 2 in 1968. So we had just learnt addition as children, and my teacher then said, now we learn multiplication and we'll start by learning the doubles, the 2 times. And she said that to double any number, it's very simple. All you do is just add that number to itself. So to double 2, you just add 2 to itself, and you have 2 plus 2. Multiplication started off making a lot of sense. But then she wrote 2 into 3 on the blackboard, and then no children knew their times tables at this point. We had only just learned addition. My teacher asked the class, who can tell me what 2 added to itself 3 times is? That's been the definition of multiplication attributed to Euclid in the English language back to February 1570. So I put my hand up. This was my premier public speaking moment in class 2. This is the first time I ever spoke on mathematics. And my teacher said, Jonathan, and I was standing up in front of the class, and I said, 2 added to itself 3 times is 8. And she said, no, it's 6. That didn't make any sense to me, because I was really good at adding. I knew how to add. I was a very good adder. Now, this is the problem that I noticed 50 years ago. 1 plus 2 plus 2 plus 2 equals 7. So 2 added to 3 times to 1 equals 7. So how could 2 added to itself 3 times be equal to 6? 2, 2, 2, 2, the sum of that is 8. So I was right. The definition of multiplication had been wrong for centuries. Now my teacher didn't like thinking that a boy who didn't know his times tables was saying that Euclid's definition of multiplication was wrong, but that's what I noticed. Now what my teacher did is she then had a number line on the blackboard. And what she did is she says, no, it's not 8. I'll show you how it's 6. And we're going to do hops of 2. So she went 2, another 2, and another 2, and sure enough, she landed at 6. And I felt very stupid, because I said it was 8. And so from that moment, I hated mathematics. Because I thought I knew how to add, and I was told multiplication is repeated addition, and we all hear that that's because of Euclid's definition, and I've got some surprising information about that. But where did my teacher on the blackboard start those hops from? She started hopping from 0. So she said to the class, who can tell me what 2 added to itself 3 times is? She should have correctly said, who can tell me what 2 added to India's 0 is 3 times? So that's what I noticed 50 years ago. The definition of multiplication gave me the wrong answer, even though it was a very precise algorithmic explanation, and 0 was missing. And so I disliked mathematics, and then I kept on coming across other things that I knew were wrong. But my teacher, I knew, was right. Because my teacher knew everything about mathematics. And that's what we expect our teachers when we're little children. As a little boy of 7 to 10, of course your teacher knows everything, because they're the teacher. So I developed what I now think of as a cognitive dissonance. I knew that 2 added to itself 3 times was 8, because there's 1 plus, there's 1 plus, and 1 plus, so it's been added 3 times to itself. I knew that 2 added to itself 3 times was 8. My teacher said it was 6, but I had to believe my teacher, so I just had no trust in numbers from that point. And then throughout the curriculum, I kept on seeing things as a recurring theme. Not only was 0 missing, but the number 1 was also missing in explanations of mathematics. So I quit my job. I did an economics degree because I didn't like mathematics. My children love mathematics though. One's doing a PhD in quantum computing, and others got a master's in science, and another son is a postgrad accountant. So they're all into numbers, but I didn't like it, so I did economics. But anyway, in 1983, I quit my job working in a management consultancy to try and fix mathematics. And I thought, if it was to be, it's up to me. It seems that no one else has noticed that the foundations of mathematics were problematic. Everyone seemed to assume that the evolution of mathematics had been a polished gem following the principle of Kaizen, constant and never-ending improvement. Well, what I'm about to perhaps reveal to you is that we need to go right back to the 7th century and start again. So that's enough of my preamble. I will now get on with the presentation. So, 1988, I was making headlines in 1987 and 1988 because I didn't know how to teach mathematics. I wasn't a trained teacher, and I didn't have any university qualifications in mathematics. So what did I start to do? Well, I started to teach children mathematics through creative visualization. I used to get the class to close their eyes and imagine fun games with the numbers in their mind, and those stories, what those children would see in their mind, would be just as memorable as if they had seen it in real life. And if I was able to convert the mathematics into stories and pictures, the children enjoyed that and they started to do well. So you can see here from this newspaper article 30 years ago that I said very, very clearly, quoted in the newspaper, "I hope to change the way the Western world teaches maths," Jonathan said. So this is me stating my lifetime purpose 30 years ago. And now I'm finally here. It's taken a long time. So this slideshow presentation represents an update after 30 years since the world reported on my promise. But bear in mind, I had begun 5 years before this. I started in 1983. But I only really started to make headlines several years later. So, a quick recap of what facts we know. In 300 BCE, the Greek Euclid of Alexandria defined multiplication as repeated addition. a into b equals a added to itself b times, and a to the power of b equals a into itself b times. 0 is very simply defined by subtraction in the elementary schools as a minus a, or n minus n, a number subtracted from itself. So if we've got 5 lollies and the 5 lollies are taken away, the number of lollies we've got left is 0 lollies. So we introduce 0 by subtraction and that's kind of a de facto definition in the elementary grades.
Hello.
We also know that the Arabic world embraced India's idea on 0 and negative numbers, and Arabic maths was then adopted by Leonardo Pisano, and yet those facts are what informs most books on the history of mathematics. And as it also happens, most books on the history of mathematics are written through a Western viewpoint, not through Eastern eyes. So you may not see that everyone is entitled to their own opinion, but not to their own facts. So we often argue and debate in mathematics about definitions and ways to appropriately solve problems, but I've kind of felt, and you've got to just forgive me because I'm outside the mathematics community. I've been doing this on my own. I've really been in my own private little world trying to figure this out for myself because I always felt stupid. In a way, I had a game. I was a detective. And I like detective shows, and somebody murdered mathematics. Don't know where, don't know when, but I reckon that maths had been murdered, and I was going to try and find out who murdered mathematics. And believe it or not, I've got 3 people that if there was a court of law, I'd put them on for trial, and they would be prosecuted. Exactly the 3 people in history. Okay, maths, in my opinion, must be rebuilt from 0. Because as a child, my teacher's definition was 2 into 3 was 2 added to itself 3 times. No, 2 into 3 is 2 added to 0 3 times. Very, very big difference in that. So, extraordinary claims require extraordinary evidence, and I hope to convince you that I've been collecting enough extraordinary evidence to at least get you to open your mind about, well, maybe we really need to not just go back to the astronomy and the mathematical astronomy, but maybe we need to go back to the very simplest mathematics that maybe Brahmagupta would have shared with his children. How might Brahmagupta have explained positives and negatives and 0 to his children? So my approach has been, because I'm a naive mathematician, I'm an autodidact, I'm kind of self-taught in a way. I was wanting to know, okay, all of the shlokas of Brahmagupta and all the verses, they're very, very, very condensed verses. But what would they have done at home to explain multiplication of positives and negatives? What games would the parents have played with their children in the oral tradition that was so strong? None of those simplest ideas I would ever have been expected to have been committed to any formal book, especially because most of the books were focused on astronomy and mathematics was a tool for the benefit of the astronomer. So remember, I'm stuck in grade 2 my entire life trying to think, how can I make mathematics make sense to a 2-year-old? And that's what I'm still attempting to do. Okay, so India's definition of 0 never made it to either the ancient Arabic world or Europe. Now that's not the story. In the Arabic world, India's 0 only came to exist as a placeholder, not as the power tool to solve simple problems like positive 3 minus positive 4, or negative 2 minus negative 4, or negative 4 minus positive 2. Now, one thing that you'll notice in the way that I present these expressions is whenever there's an adjective, I superscript the adjective. And by adjective, I mean positive and negative. And the verbs in the grammar stay standard case. Because children are always being confused when you have things like minus negative 3, and it looks like minus minus, and they get incredibly confused. one of the things I do quite often to demonstrate that the grammar needs to be fixed is ask adults, not mathematicians, but to ask adults, tell me, what's -7 minus -4? And when I ask adults in Australia, maybe it might be different in India, but when I ask what is -7 minus -4, most adults answer -11. Because they get confused with the double negative and they think that means they've got to add on and make it bigger. But here's the difference. If I ask nearly every 7-year-old child I meet, which is my level of grade 2 understanding, because we did subtraction as well before multiplication, if I was asked in grade 2, Jonathan, what's 7 negatives take away 4 negatives? I would have said 3 negatives. And I would have been right. Because the language that we have been using is grammatically garbage. -7 minus -7 is equivalent to saying the fast blue minus the slow green. Children need concrete explanations of mathematics. So by talking about 7 negatives, the children instantly can treat the negatives as nouns, and the numbers simply become the adjective that describe the count of the noun. So 7 negatives minus 3 negatives is incredibly simple for everyone. So in the presentation that you're going to see here today, sometimes I'm going to change between +4 and then I might also say 4 positives. It means exactly the same thing. Okay, so here's al-Khwarizmi. I'll read it. So they made 9 symbols, which are these. 9, 8, 7, 6, 5, 4, 3, 2, 1. Because 1 is the root of all number and is outside number, it is the root of number because every number is found by it. But it, 1, is outside number because it is found by itself. I mean, without any other number. Now, what number hasn't al-Khwarizmi mentioned yet? It's the same number that wasn't mentioned for me in grade 2, 0. And al-Khwarizmi wrote the book on Hindu arithmetic, and he wrote that, by the way, after his book on algebra. And he's not really talking about 0. And we just assumed that he was very competent. Okay, so this guy here, al-Yuklidisi, my pronunciation, I've never heard these names, so I'm just guessing. Why is 0 multiplied by 0 equal to 0? And 0 multiplied by any letter is 0. We say that by multiplying 0 by 0, the aim is only to occupy the place. The same applies for multiplying the letter by 0. We multiply the letter by 0 to occupy the place and tell that there is a place and that it is empty. Okay, so this is only a little bit of the evidence, but this is indicating al-Khwarizmi, and by the way, I'll mention this chap here, al-Yuklidisi. He was instrumental in the passage of Indian mathematics, and I'm aware I'm talking to the experts, so please do correct me anytime I'm wrong. But this chap was instrumental in changing the form of the gunana, the killing method, where you are rubbing out the calculation as you go along. He transformed the Indian method of multiplication into the form that we use today, where you write out the multiplicator, you've got the multiplier, and then you write out a series of partial products, and then you sum the partial products. So that's the work of this gentleman. So he was very important in reformatting the Indian logic to be the similar styles that we use today. Okay, so 200 years after Brahmagupta, al-Khwarizmi did not accept 1 as a number. 0 as a number? Never. 300 years after Brahmagupta, al-Yuklidisi accepted India's 0 as a placeholder, yet not a number. Why? Al-Yuklidisi means the Euclidist. He was known for his skill in studying the Greek geometry of Euclid and translating it into Arabic. So around 300 BCE, Euclid defined number as a multitude of units. So Euclid's definition of number came before 0 and 1 were numbers. So this guy, Al-Euclidesi, 300 years after Brahmagupta, his entire mindset was in Euclidean definitions of number. And number had to be a multitude of units, and he already knew that his predecessors like Al-Khwarizmi had already agreed that 1 was not a number, because 1 was a unit, and so on. So nowhere in the discussion of Hindu arithmetic do we see 0 even understood as a number. And yet the story is that the Arabs took the Hindu arithmetic, and probably a lot else as well. They developed their algebraic ideas, and the whole bundle then made its way via North Africa to Leonardo Pisano, and he brought it into Europe in the early 13th century, wrote Liber Abaci, and that's the transmission story that seems to inform most history books. But I'm not liking that story at all. Okay, as we will see, India defines 0 as the sum of opposing negative and positive numbers with the same multitude or magnitude. So that's like saying 4 negatives and 4 positives are 0. Okay? It's a very symmetric, balanced sort of approach, similar to the Chinese philosophy before it of yin and yang, equal and opposite. So, if Arabic and European writers in medieval times really understood India's 0, where are all the negative numbers in their writings? Because 0 was defined as the sum of equal numbers or magnitudes of positive and negative. So surely, if 0 was a number, you'd be writing all about all the positives and negatives that define 0. But we, as you probably know, don't see any writings. Okay, so this is a quote from Professor Geoffrey Oakes. So he's an expert on medieval Arabic mathematics, and this is via email to me recently. Well, I'll just read it. I have read a few dozen medieval Arabic books on arithmetic and algebra, and there is no hint of negative numbers in any of them. 0, 2, whoa. Okay. 0, 2 was not regarded to be a number, but was merely the placeholder for an empty place in the representation of a number in Arabic, brackets Indian notation. All numbers in Arabic arithmetic were positive. No Arabic author, to my knowledge, ever even contemplated the existence of negative numbers. And yet 0 is defined as the sum of positive and negative. And yet all the Arabic world is only focused on the positive. Sounds like a philosophy. And that's, I'm just simply waiting for permission from Professor Oakes to quote it, so I've just got it, yeah, anyway, I've told you who it is anyway. So inside we discover inconvenient truths. Truths you may not know. India's primary level explanations of maths date back to the Greek maths ideas taught in 16th century England. India's maths is thus built on Greek geometrical foundations dating back to 300 BCE, when negatives 0 and 1 were not numbers, at least in Greece. India's newer maths, featuring base 10, positional notation, negative 0 and 1, came 1,000 years after Greek maths of 300 BCE. And I've just got a question. Yet, is it understood in India? The most important numbers are 0 and 1, and we think of computers running on binary, yet England didn't include 0 and 1 in their definitions of multiplication, now a into b, and exponentiation, now a to the power of b. So explanations of multiplication and exponentiation have been wrong for centuries. So that's another thing I noticed, is that the definitions of exponentiation didn't make any sense to me either. And that's because they were deliberate mistranslations. Okay, so we go back to Brahmagupta, astronomer and mathematician, who wrote the Brahmasputa Siddhanta in 628. So for this talk, Brahmagupta's laws of positives, negatives and zero have been freshly analysed, and you all know the translation of Brahmagupta's chapter 18 on algebra, verses 30 to 35. You probably almost know it by heart. But what I'm saying is I've not only analysed the Sanskrit, I've also attempted to interpret it through a child's point of view, and also literally questioning, why would Brahmagupta be writing these laws? What is he trying to tell us from a way that we can then share with children? So it's not just analysis, there's also my interpretation in this, but my interpretations are all consistent with the laws that we'll go through. So I found this at the British Library, because this is the 1902 version of the Brahma's Gupta Siddhanta, which is relatively rare. I, as it happens, also found it on microfilm in Chicago, and the microfilm was then flown to Chennai, and then they had a microfiche reader in Chennai. They then converted the microfilm into 248 bitmap images, which then I cleaned up and converted into a PDF. So this version of Brahmagupta's work is also available on the internet if you just do some Google searches. So that was a fun little side project. Okay, so what I did is I simply, from chapter 18 on algebra, the laws of positive, negative and zero, I lined up sequentially every single line of the Sanskrit. And this is both the writing of Brahmagupta and all the commentary of, I don't know how to pronounce his name, Jadavpur. Okay, well, regardless of how his name's pronounced, he did commentary, and I've analysed Brahmagupta's writings on the laws, I call them laws, and also the commentary. Now, I didn't do this, I obviously had a lot of help from people, and I acknowledged them a little later in this presentation. So, from a naive point of view, I now extract the laws out of Brahmagupta. And you'll be familiar with these, but I kind of lay out a little bit of a roadmap for primary school teachers to start to share them with young children. So the AL1 simply means addition law number 1. So the first addition law is very simple, positive plus positive is positive. Addition law 2, negative plus negative is negative. And if you see anything, please give me feedback, because I'm also here to get feedback and to learn. Addition law 3, positive plus negative is the difference between the positive and the negative. Addition law 4, when positive and negative are equal, the sum is 0. And just as a comment for people in the West, I just point out that shunya, 0, is neither positive nor negative, but forms the boundary line between the two kinds, being the sum of two equal but opposite quantities. And this is consistent with Chinese mathematics and their odd numeral arithmetic, which was before this by several centuries, without 0, but with places on their counting and calculation boards. So we then continue on to addition law number 5. Positive plus 0 is positive, negative plus 0 is negative, and 0 plus 0 is 0. Now, I'm thinking from grade 2, why does he keep on going on about 0? We ignore that because we know that if you add 0 to any number, if you subtract 0 from any number, it doesn't do anything, so we ignore it. But why is he so much talking about zeros all the time? And then it finally dawned on me that I can use the prevalence of 0 in his addition laws to solve mathematical problems by, believe it or not, doing things like adding 0 to a 0. I know it sounds strange, but I'll explain what I mean by adding 0 to 0 to solve problems. Okay, so there's addition law number 5 in its entirety. Basically, just talking about 0 being the additive identity element. Now, as it happens, both of the identity elements, 0 and 1, have been missing in the foundations of modern mathematics. 0 and 1 have been missing from the foundations of modern mathematics because we built our pedagogies from Greek geometry, principally book 7 of Euclid, for example, elements, in which 0 didn't exist, 1 was a unit and not a number. Okay, so there are the Brahmagupta's 5 addition laws that we don't just look at and memorise, we then start to play with them. So, we then move on to Brahmagupta's subtraction laws. And very simple, subtraction law number 1, if smaller positive is subtracted from larger positive, the result is positive. If smaller negative is subtracted from larger negative, the result is negative. Now, you don't see any subtractions of negative numbers in any medieval writings. But straight away, why does he have all these laws of subtracting when he's talking about subtracting smaller negatives from larger negatives? And later he talks about subtracting larger negatives from smaller negatives and getting a positive. So the entire structural foundation of his laws are equally balanced between positive and negative, and I have never found any medieval references that treat negative numbers as equals to positive numbers. They're all based on Babylonian or Greek principles, not India's. Subtraction law 3, if a larger negative or positive is to be subtracted from a smaller negative or positive, the sign of their difference is reversed. Negative becomes positive and positive negative. A negative minus 0 is negative, a positive minus 0 is positive, and 0 minus 0 is 0. So again, all of these zeros again in simple subtraction, and I'm thinking, why aren't we just ignoring 0 and like moving on? Like, that's what the world's done. We know that 0 is also the subtractive identity element as well as the additive identity element. So let's just move on. But Brahmagupta is going on and on and on about it. When a positive is subtracted from a negative or a negative from a positive, then it is to be added. So there are Brahmagupta's 5 subtraction laws. And I'll just remind you that you'll all get copies of this presentation, so you don't have to remember what you're seeing here. You'll get the slideshow. So seeing is believing, applying Brahmagupta's 5 addition laws. So in terms of developing the appropriate pedagogies for young children, you may be familiar, or maybe this is below your level, but you've got the ideas of the concrete, the abstract, and then the symbolic. So if we're going to start to introduce Brahmagupta's laws, we need to start off at a concrete instantiation of those laws and then move into the abstract and the symbolic. So I've tried to develop a sensible pedagogy for classes maybe 2 to 6, 2 to 8. Obviously the curriculum designers will have to take this on board and develop it accordingly. But let's get on to it. So here we've got a car battery, and while I've got a car battery and an Indian maths presentation, I just simply want you to lock in that the negative terminal on a car battery is black and the positive terminal on a car battery is red. And they're the colour codes that I'm going to be using in the pictures that follow. That's also exactly the same colour coding that China used with their odd numeral arithmetic as well in the 2nd century BC. Okay, so here we start to just do the concrete instantiations. And we can also do this with building blocks and physical toys as well. So positive plus positive is positive. Negative plus negative is negative. So it's just as much stories about negative numbers as it is positive numbers, which we never saw in the Renaissance writers. Okay. Positive plus negative is the difference. So we've got 4 positives, and then we're adding 3 negatives, and then you can just see what the difference is. That's the difference. So we start off with the symbolic representation of the laws. The children can have a discussion about how are they different, and they'll say that we've got 1 more red than black, and so that's the difference. So positive 4 plus negative 3 equals positive 1. Positive 2 plus negative 4, the difference is negative 2 or 2 negatives. So we can start to see some very simple pedagogies emerging from Brahmagupta's laws that are obvious and yet basically completely missing from the way that we'd instruct young children. Typically in Australia, we don't really start to talk about negative numbers until class 7, and some schools maybe even class 8. Why? Because it's incredibly confusing. Okay, so this is Podo the puppy. And she was my real puppy. So my intention is to give every child in India access to free PDF mathematics books by the end of the year 2020. So they'll have all of the laws of arithmetic repurposed based on the laws of Brahmagupta, and they'll all be cartoon storybooks where the animals do things with quantities, and you can see what the animals are doing with quantities, and then the teacher or the parent can then start to then convert it into mathematics. So the metaphor here is that this is 3 negatives. Because remember the blacks were the negatives? And here we've got 1, 2, 3, 4, 5, 6, 7. So let's see what happens when Podo the puppy puts 7 positives with 3 negatives. Should we let it drop? Yeah, let's let it drop. Boom. Okay, so negative 3 plus positive 7 equals positive 4. And many children will have happy memories, or maybe you even do as well, of playing with a bucket and spade. Digging a hole with your spade, and maybe you've got a square-sided bucket, filling up the bucket, turning up the bucket the other way and making a brick. Well, this is a way that we can start to model the laws of Brahmagupta through fun metaphors. And as it happens, Podo the puppy also does advanced things based on the Shulva Sutras, like squaring a circle with rope. So there are videos on YouTube for that. So Podo the puppy starts off with how to add positive and negatives, but she'll also be teaching aspects of geometry and maybe later on trigonometry and so on, because everybody loves cartoons when they're children. Okay, so when positive and negative, when positive and negative are equal, the sum is 0. So with this addition, we had 4 positives and 3 negatives. The difference is 1 positive, but also we can just eliminate this because we know that by addition law number 4 that that's 0. So we can straight away know that the difference is going to be 1 positive. So we start to build up understandings of how to think mathematically by being flexible in ways that we apply the laws to different situations. So here we've got 2 positives and 4 negatives. These 2 negatives, but we can straight away start to look at that and basically ignore it and know straight away that the answer is going to be 2 negatives. So positive plus 0 is positive, negative plus 0 is negative, and now we'll start to play with the laws of Brahmagupta with the difficult area of subtractions of integers, which confuses people, which is why I said negative 7 minus negative 4. Adults around the world find that really difficult to get their head around. Okay, if a smaller positive is subtracted from a larger positive, the result is positive. Okay, obvious. Larger positive minus smaller positive is positive. Smaller negative subtracted from larger negative, the result is negative. And again, Brahmagupta is just as much about negative number theory as it is positive number theory. And the world's pedagogies are only based on the red, not the black. Okay, so larger negative minus smaller negative is negative. Okay, this one is where it starts to get fun. Subtraction law number 3. This one and addition law number 4 are the real gems when it comes to teaching children arithmetic. So if a larger positive is to be subtracted from a smaller positive, the sign of their difference is reversed and positive becomes negative. So we've got 3 positives and we want to take away 4 positives. What? 3 positives minus 4 positives? We don't have enough positives. How can we take 4 positives? We've got 4, we can't take 4 away from them, we don't have enough. So we apply addition law number 4 and addition law number 5. So what we do is we add 0. So there we have added 0 in the form of 4 negatives and 4 positives. And we know from all the laws that any time you add 0 to a positive, it doesn't change the number. But now we can subtract those 4 positives from the 4 positives embedded in our 0. So we subtract now the 4 positives, we get this, we simplify because we notice that we've got a 0. And so positive 3 minus positive 4 gives you negative 1. So this can become a series of games. And pretty soon the children will move from the games to understanding the laws. 3 positives minus 4 positives is 1 negative, because we added 0 to solve the problem. Okay, so we've got -2 minus -4. 2 negatives minus 4 negatives. We don't have enough negatives, so what we're going to do is we're going to add 0. We add 0, we subtract, we simplify, so -2 minus -4 is +2. And this is the sort of pedagogy or lesson plans that would be entirely appropriate possibly for class 3, as opposed to maybe being class 7 at the moment. So you can bring some of the higher levels of basic mathematics to the lower grades, and I would say that you must start teaching positives and negatives at the same time. Because if you only start teaching the positives and then introduce the negatives, everyone gets confused, especially the teachers. But if you start off with the ideas of the simple idea of the bucket and spade, and a hole and a bump go together, they can only go together. You go to the beach in your mind, you've got ground level 0, and you start to change ground level 0 into a series of holes, which are negatives, and the bricks, which are the positives. Okay, so 4 negatives minus 0 negatives is 4 negatives, 3 positives minus 0 positives is 3 positives. I just have to go through all the laws. When a positive is subtracted from a negative, then it is to be added. Add 0, because we don't have any positives to subtract from -4. So we've got 4 negatives, and we're trying to take away 2 positives, which we don't have. So we add 0, we subtract, and we get the answer. And you saw that when I was down at Andhra Pradesh, I taught 558 children in classes 7 to 9 in 2 days. I left that problem with their teachers to solve as a game. And I also left them 200 red chips and 200 black chips, so they could play all the games with their little chips, like plastic counters, as a game. Okay, so the multiplication laws. The product of a negative and positive is negative. Now just remind you that the definition that the Western world has been following, and pretty much I'd say the whole world, is A into B is A added to itself B times. And in many books written by scholars, they say as per Euclid. Euclid defined multiplication as repeated addition. Whoa. I've got some really exciting news for you. Okay, Brahmagupta multiplies positives and negatives by either adding to 0 multiple times or subtracting from 0 multiple times. So, this is how you start to read multiplication the Indian way. Forget the Western way, it's complete garbage. So negative A into positive B equals negative A added to 0 B times. And why is the multiplicand added to 0? Because it's the sign of the multiplier that determines what action we're going to do to the multiplicand with respect to 0. So, if we take an example of -2 into +3, we now know it actually gets decoded correctly the Indian way as -2 added to 0 3 times. So, -2 into +3 is -2 added to 0 3 times. So there's our 0. So let's start adding -2's. We've added -2 once, we've added -2 twice, we've added -2 3 times. That's it, the answer is -6. Okay, so then this might be a year later in the curriculum. So in the lower grades we'll get them used to playing the games with the integers, and then we obviously at some stage move on to the symbols. So 2 into +3 equals -2 into 0 plus 1 plus 1 plus 1. Because that's what I noticed 50 years ago, that we always need to take into account that we start building number from 0. And 0, if we treat it as a number, is the orgend from which we add the addend. Maybe you don't use the word orgend here, but orgend is the old word for the first number in an addition. And the second one was the addend that you add on to the orgend. Okay, so 2 into +3 equals 0 plus -2 plus -2 plus -2 equals 0 plus -6. So negative 2 into positive 3 equals negative 6. So multiplication distributes over addition. Now, when I asked professors, why do we define negative times negative equals positive, the most common answer that I got is that we define negative times negative is positive in order that the distributive property of multiplication holds. I don't know what that means. Like, I just want a simple, just tell me why so I can understand it. Don't tell me that we define it that way in order that another whole lot of things will work. And as it happens, the entire understanding of the history of minus into minus and negative into negative is completely wrong as well. Okay, Brahmagupta did not say the product of a positive and a negative is negative. However, we can demonstrate this via his laws. Maybe he thought it was obvious. Maybe he didn't have enough words to put into the rhymes to include this one in the metrical beat and the rhythm. But anyway, let's do it. Positive 2 into negative 3. So we now know that positive 2 into negative 3, positive a into negative b, means positive a subtracted from 0b times. Why are we now subtracting the multiplicand? Because of the sign of the multiplier. And these are the things that we've never seen defined. We've only ever seen definitions of multiplication on the positive naturals. I've looked, and I've never found any definition. I found one. I found one in an engineering magazine. But I won't go into that. But I have really, really looked hard. Okay, so we've got positive 2 into negative 3 is positive 2 subtracted from 0 3 times. So there's our 0. But we don't have any positive 2's to subtract from 0. So what do we do to 0? We add 0 to 0. So we've just added 0 to 0 in the form of 6 positives and 6 negatives. So now we can start subtracting our positive 2's because we know from Brahmagupta that 0 added to 0 is 0. So positive 2 subtracted from 0 3 times. Okay, positive 2 subtracted once, positive 2 subtracted twice, positive 2 subtracted 3 times, and there's the answer. We get a blank screen. Okay, so again, what we do is we go from the concrete to the symbolic. So we just, now this is an important point. Teachers know that multiplication distributes across addition. But if you ask, is that it? No teacher will say, well, also multiplication distributes over subtraction. Why? Because of all of the history of number theories being based on the positive naturals, from Grassmann, Dedekind, Peano, all the others, the number theory was based on positive naturals. And so we just completely get into this adding and positive mindset, and we've completely lost the symmetrical logic behind India's mathematics. So yes, multiplication distributes over subtraction as well. So positive 2 into negative 3 equals positive 2 into 0 minus positive 1 minus positive 1 minus positive 1, which becomes that, which becomes that. Now, we've got 6 positives taken away from 0, which we can't do, so we add 0 to 0, and simplify. So positive 2 into negative 3 equals negative 6. So this is a demonstration of why the product of 2 negatives is positive. So we've got negative 1 into negative 1 equals positive 1, and we've got a process, a sequence where we go through to prove to children that it's mathematics. And aren't we clever mathematicians because we can do all of this and we understand it all, and the children are just completely bamboozled. So the Indian way of proving it is very different. Negative a into negative b is negative a subtracted from 0b times. So the way that we now read negative 1 into negative 1 is negative 1 subtracted from 0 one time. So there we've got 0, and we've got a 0 embedded inside the 0, but it's still 0. So what we do is we now subtract negative 1 from 0 one time, and we will now prove that negative into negative equals positive, because let's subtract the negative 1, and there we've got an Indian proof of negative 1 into negative 1 equals positive 1. Now children will understand that because they'll be able to play that as a simple game. and they'll be used to adding zeros to zeros and using Brahmagupta's power tools, his laws, to solve problems. So you can teach this probably to a class 6 class easily, and they'll understand this very simple logical proof. So therefore, -1 into -1 equals +1. And if you compare that to the proof that I wrote up in a mathematics magazine, I know that I prefer the Indian way versus the Western way that I wrote up. So the product of two positives is positive, which is simple. We've got the product of 0 and a negative, 0 and a positive, and of two zeros is 0. Okay, and then we've got the summary for the multiplication laws. Now, this is me imagining I'm now assessing the world's models of mathematics since Brahmagupta. So all I've done is I've looked at the simple integer arithmetic, and here you see on the first row I've got addition, I've got subtraction, multiplication and division. And I've chosen simple aliquot division so there's no remainders. Now what I've then done is I've said to the world, everywhere there's a green, I reckon the world has done an acceptable job in developing pedagogies that explain these types of integer operations. Where the cells are in yellow, I am failing the evolution of mathematics from Brahmagupta to now, and this one here is just absent. There's no, this doesn't appear in mathematics books. They just kind of like hope that the question never gets asked, and I'll go over the reason why they hope the question never gets asked. So we now go quickly onto the division laws. There they are, the 4 division laws. And here I just acknowledge the various people. So I've got many people that I've been emailing over the years, and this part of my interpretation has taken me 5 years to kind of go from the very first emails and translations to finally thinking how I can translate it into something that really makes sense to elementary level maths teachers. Okay, so why do I only quote the non-zero division laws? Whilst a 0 divided by any non-zero number is 0, Brahmagupta says a non-zero number divided by 0 remains 0 divided. So he doesn't really have anything conclusive to say in the 7th century, which is still a darn fine effort because everything else is spot on. But of course, commentators such as Bhaskara II, the Bhaskaracharya, suggested n over 0 is either infinite or indeterminate. So later on, you can move on from Brahmagupta to some of the later mathematicians from India to discuss their considerations of zeros and infinite. Okay, so here we've got the models of division. We've got positive 12 divided by positive 4, and the first model that the teachers have is called the equal groups model. At college, they'll call it the partitive model, but when they talk to children, they'll call it the equal groups model. So it just goes like this. If you've got 12 things in 4 equal groups, how many things go in each group? And the answer is 3 things go in each group. So 12 by 4 equals 3 things with that model. Very simple. So we can give a tick to the partitive model. The quantitative model is the repeated subtraction model, and it goes like this. If you have 12 things, how many times can you subtract 4 things? Well, you can subtract 4 things from 12 things 3 times until you've got 0 things. So therefore 12 by 4 equals 3 times. So we've actually got different models here. So we're actually mixing up the quotient and the divisor, and you can start to look and see some more complexity in here. But the quantitative model for positive numbers also works. So both models work on the positive numbers. But when we look at other combinations of the integers, we see that some of them don't work. Equal groups model doesn't work over here, because how can you have -4 groups to put 12 negatives into? The repeated subtraction here, you've got -12. Well, if you do the repeated subtraction, you go -12 minus +4, well, that gives you -16. Minus -4 gives you -20, minus -4 gives you 24, you're never going to get to 0. So you can't use that one. So we look at the problematic positive 12 by negative 4, and we look at the equal groups. If you've got 12 positive things and negative 4 groups, how many things go in each group? You can't have a negative number of groups to put things into. So the model fails. With the repeated subtraction model, if you've got 12 positive things, how many times can you take away 4 negative things? You can't subtract 4 negative things from positive things. And if you just try the number approach, positive 12 minus negative 4 equals 16, minus negative 4 equals 20, minus negative 4 equals 24, i.e. you go the wrong way and you never get to 0. So the equal groups model fails, and also the repeated subtraction model fails. So I don't fail this pedagogy, it's just completely missing after pretty much 1,400 years, which is why I think that the world has not done a good enough job for children at elementary school. I'm complaining. Okay, so now I start to talk about a new model that I developed, which is a blend of Brahmagupta's integer laws with proportion theory of Greece. So I say numbers are counts or measures of standard units, and we choose positive 1 as our standard unit. Now with Brahmagupta, we could just as easily choose negative 1 as our standard unit, and provided we stuck to our standard unit of negative 1, all of the mathematics will still work out and be completely consistent. Okay, so 1 is the multiplicative identity and the divisional identity. So all numbers are measured by the unit called 1, so thus all numbers are ratios of n to the standard unit. So basically I'm saying that all numbers can be considered ratios of n by 1. Because numbers are multitudes of units. I mean, that even goes back to Euclid. So our goal is to convert positive 12 by negative 4 into the form n by 1. So we look at the denominator, and to make negative 4 be positive 1, we take one of the 4 parts of negative 4, which is negative 1, and we subtract it from 0 to get positive 1. So we're still using the ideas of Brahmagupta here, which is simply, so to make negative 4 be positive 1, we take one of the 4 parts of negative 4, which is negative 1, and subtract it from 0, and we get positive 1. So what we've done is we took one of 4 parts of that, which is negative 1, we subtract it from 0, which changes the colour. It's just a colour swapping game for the children, and that becomes positive 1. That's what we did to the denominator. So then, whatever we do to the denominator, we've got to do to the numerator. So with the numerator, we take one of the 4 parts of positive 12, which is positive 3, and we subtract it from 0, and we get negative 3. So we've kept the problem of division within the realm of division, and we haven't had to ignore the division and convert it into a missing factor problem. Because what the standard approach is in the classrooms is, if a teacher is ever asked what's positive 12 by negative 4, they'll say, we'll teach you the laws of sign, and then we'll convert it into multiplication, and then we'll say what number into negative 4 will give you positive 12. And if you've learnt the laws of sign, then you've got to use deduction to say, well, process of elimination means I know it's negative into negative gives positive, so I've got negative 4, it's got to be a negative number, and the only one that makes sense is negative 3. That's a really convoluted way, and it also completely ignores the fact that you're talking about a division problem. And then just turning it into a multiplication problem and avoiding it altogether. So, positive 12 by negative 4, 0 minus the numerator by 0 minus the denominator gives us a very quick, simple resolution that the answer is negative 3. Okay, so in this kind of newish pedagogy I've called proportional covariation, whatever we do to the unit 1 to make the multiplier B, we do to the multiplicand A to make the product C. So now I know my ABCs. Little children start to learn the alphabet with sing-song, just like they did in the 7th century schlockers and so on. So There are actually 4 numbers in the operations of multiplication and division, not 3. We've only, in multiplication, known 2 factors and 1 product. But multiplication, if you understand it correctly via Euclid, is a proportional concept, nothing to do with addition. In fact, I may as well just continue. Can you continue that thought for a moment? All of the books, like the development of multiplicative thinking, say Euclid defined multiplication as repeated addition. Well, I've checked Euclid's book 7 in about 18 languages, and I've had experts comb over it, all of book 7, all of the propositions that involve multiplication. The number of times that Euclid uses the word add, adding, addition, adds, in all of his propositions involving multiplication, the number of times Euclid mentions add in the context of multiplication is 0. And yet we say Euclid defined multiplication as repeated addition. No, Euclid never added when he had any proposition that involves multiplication. Now you're saying, hey Jonathan, something doesn't make any sense here. And I figured out what it was. You see, what happened is, back in 1570, the chap who translated Euclid's Elements from the ancient Greek into English, he wasn't a professor of Latin or a professor of ancient Greek. He wasn't even a professor of mathematics. The man who translated Euclid's Elements for the first time from ancient Greek into English was a shopkeeper. And guess what? That shopkeeper thought, I can explain multiplication better than Euclid. So the shopkeeper changed Euclid's definition of multiplication when it was the very first time it appeared in the English language. And that shopkeeper was a man called Henry Billingsley. And he deliberately changed the translation of Euclid because he was told to by another man called John Dee. He was a famous magician and astrologer and friends with Queen Elizabeth. Now Henry, the shopkeeper, he was a social climber. And he thought, well, I'll get a lot of respect by translating Euclid into English when no one else has done that before me. They'd already translated it, by the way, into Italian, French and German. And they'd already translated Euclid's definition of multiplication correctly into Italian, French and German. But when it went into English, a shopkeeper did the translation, and it was wrong. Why did John Dee suggest it get changed to Henry Billingsley? Well, John Dee got the idea from Petrus de la Ramée, a French philosopher. So they would be the 3 gentlemen that I'd put on trial for murdering multiplication in the first instance. But as we saw, India's 0 never even got through the Arabic world. Bit of a diversion, but that's the thing that did my head in grade 2. That wasn't Euclid, and my teacher thought she was giving Euclid's added to a self-definition. Nah. Totally different. Okay, so in division, as you'd expect, instead of the ratio of 1 to b determining what we do to a to c, it's the ratio of b to 1 that determines what we do to a to c. So whatever we do to the divisor b to make the unit 1, we do to the dividend a to make the quotient c. Okay, so here's a visual representation, and this is what children might do in, say, class 3 to solve positive 12 by negative 4. The impossible problem that's never been given an appropriate maths lesson since Brahmagupta. So we've got 4 negatives, and so as 4 negatives are 1 positive, what did we do? We took one of those 4 equal parts, which is negative 1. We played the game of subtracting from 0, which just means changing the colour. So whatever we do here, we have to do, so this is the divisor, that's the unit. Whatever we do to b to 1, we do to a to get c. So we take one of the 4 equal parts, which is this column here, we subtract it from 0, and we get the answer of negative 3. So children have got a fun little game they can start to play based on the kind of embedded pedagogies in Brahmagupta's laws. So now we can finally say that we've got all 4 combinations of integer multiplication and division sorted out, and now we can start to use positive 12 by negative 4. We've got very simple games using proportional covariation. And this is from a double-blind peer-reviewed paper that was published in Hungary last year. So what did India do? They love putting everything to verse. So what I've done is I've translated the essence of proportional covariation into a song. And when I was touring the schools in Andhra Pradesh, all of the children, after 30 seconds, started to sing along in English, even though their language at home was Telugu. So, here we go. So you can see over here, this is all about explaining A into B equals C, and A by B equals C. And this is consistent from the positive naturals all the way to the real number system for the first time. So here we go, the multiplay song. Multiplying can be fun, you see. Do to A as one may be. Division, you see, is lots of fun. Do to A as B made one. Multiplying can be fun, you see. Do to A as one made B. Okay, now believe it or not, I had trouble in the classroom after that song. They kept on singing. I was trying to go on to the next slide, and they were still wanting to sing the song. And do you know why they wanted to sing the song? Because they know it as Bar Bar Black Sheep. So every child on the world already knows the music to the multiplay song. And this is the structural foundations of proportional covariation that explains multiplication and division on the real number system. Okay, so I'll just go over a couple more pictures. -2 to -3. What do we do to the standard unit 1 to make the multiplier -3? We place 3 units and then subtract them from 0 to make the multiplier -3. So what do we do to the multiplicand? This number, -2, to make the product. We place 3 multiplicands and subtract them from 0 to make the product +6. So this is all about adding to 0 and subtracting from 0, which is what Brahmagupta's laws are letting us know we can do with children. Okay, so I'm not going to go over every slide now because I've got some really good stuff coming up. But what I do is I give children, or more, I give their teachers, I give them multi-maths. And they get their little red chips and black chips and they can just play the games on the multi-maths. So you can see how the games work out. And so this is the resource that the teachers would get. They've got a proportional covariation multi-mat. So whatever we do to the unit 1 to make the multiplier B, we do to the number here to make the number here. So it's like whatever we've done here, we do there. And there's also the divi mat as well. So whatever we do to the unit 1 to make the divisor, we do to the dividend to get the, we do to the C to get the A. I might have to double check that one. And also on that slide, I also have dots on them because the dots introduce the concept of ratio. So then we'll be able to say that number to that number equals that number to that number to that number equals that number to that number into that number equals that number into that number, and you get all sorts of lessons coming out of it. You're introducing simple ratio patterns, and also when you get into that number times that number equals that number to that number, you'll get the children to create their multiplication sign in the middle of the multi-mat. Okay, so now, imagine if the world had understood India's mathematics, but I'm saying the world never did. So we've got Brahmagupta from then, we've got René Descartes. Now, you probably know of the Cartesian product, and the school teachers in Australia, I don't know if it's the same here, but in Australia the Cartesian product is usually given that if Jonathan has got 6 different colour shirts, and 4 different colour pants, how many different outfits can Jonathan wear? And that's known as the Cartesian product. Is that the same here? Not sure? Okay, yes, okay. Now, you can see, in fact, you can't really see the dates, but Rene Descartes is exactly 1,000 years after Brahmagupta. So Brahmagupta was 598, he was born. Rene Descartes was 1,596, he was born. Brahmagupta died 668. Descartes died almost 1,000 years later. So their lives are parallel but separated by 1,000 years of mathematical evolution that never happened. So this is what happens if we started to rebuild the history. Imagine that we can go back in time, back to the future, and do maths all over again. Well, this is Rene Descartes' first diagram that explains multiplication. So it's a little bit difficult, so I'll just explain exactly what's going on. The translation is, for example, let AB be taken as unity. So this distance here to here is the unit 1. And let it be required to multiply BD, the multiplicand. So BD is the multiplicand, the number to be multiplied, by BC. And so BC is the multiplier. I have only to join the points A and C, so it joins the points there to there, which is the ratio of the unit to the multiplier, and draw DE parallel to AC. So he draws a parallel line here from point D, which is his multiplicand, and by similar triangles, he works out the product, which is E, which is the magnitude B to E. So that is Cartesian multiplication. It's nothing to do with how many coloured shirts and pants I've got. That is how Rene Descartes introduced multiplication, with a huge innovation, because for the first time he started talking about 1 in a diagram from Euclid. So I think this is from book 6. Descartes stole it from book 6 of Euclid's Elements, and the only thing that he did different is he introduced 1 into his Euclidean diagram. So what I will do now is I will hop over to my computer and I will change to something else. So now we are on my laptop computer. We're not in the slideshow. So I've color-coded it. So this blue line along here is the multiplicand, BD. The multiplier is this line here. It's a bit hard to see, but there's a dashed green line there. The product is the red line that goes all the way up to there. And unity is still this distance from there. Unity is always going to be fixed because it's a standard unit. And all I've done is I've marked an origin from where these two lines intersect. Okay? And coincidentally, origin also looks a bit like 0. So I'm kind of cheating and fudging and putting in a 0 into Rene Descartes as well as having number 1. Okay, so what we do is let's reduce the multiplier. So as we reduce the multiplier, you can see that the product also reduces, because that's a principle of the similar triangles. So I'll put that back to where it was, and what we can also experiment with is we can then play with the multiplicand, we can then reduce the multiplicand, and you can also see that the product varies in proportion, because multiplication is a proportional concept, nothing to do with repeated addition nonsense that a shopkeeper creates. So the question I always get asked, which is the question I want people to ask, is what happens if you make the multiplier a negative number? So let's do it. So we reduce the multiplier back to the origin, which is my now 0 point. And if we continue to make the multiplier negative, we see that the product heads off in a negative direction. And similarly, if we reduce the multiplicand back to the origin, the product becomes nothing. We continue it on the other direction to a negative multiplicand, the product heads off in an opposite direction. Now, under Indian mathematics, this would have been blindingly obvious, because a line going that way has an equal and opposite magnitude of a line going that way. Like, duh. But it never occurred to people in either medieval or Renaissance Europe. They just didn't get this whole thing about that 0 point being the midpoint of magnitudes. They just thought, how could we have a line less than nothing? It makes no sense to have negative line segments. You can't have a line that's smaller than nothing. So the entire head was exploding from centuries with nonsense. Okay, now I know what you're waiting for me to do. Both of them now become negative. So what we do, I can't drag both at the same time, I wish I could. So we've now made the multiplier negative by introducing Brahmagupta's logical principles. We now have the multiplicand negative, and there we have a new geometric proof of why negative line segments, one negative line segment into another negative line segment will give you a positive line segment. So this is the stuff that never emerged because India's 0 never got out of the Arabic world. Okay? So this is the start of what we now know as the Cartesian plane. So I'm now jumping over to today, and this is now our Cartesian plane, which you can see is totally different from René Descartes' original 2 lines. Totally different. But the mathematics is exactly the same. So we've got a standard unit, we've got our blue multiplicand, and as I chop and change the multiplicand, you can see that the product changes. So if I've got 2 positives now, I've got this is the multiplier here, the green again, and so there we go. So as I increase the multiplier, the product gets bigger. As I reduce the multiplier, the product gets smaller. Similarly, as I increase the multiplicand, the product gets larger. As I reduce the multiplicand, the product gets smaller. Okay, here comes the fun. We now go to a negative multiplicand, and we see through similarity that the product becomes negative. Woohoo! Here comes the fun. I still play with this. We now have the negative multiplier and the negative multiplicand, and we see the pedagogies that haven't yet emerged because Indian mathematics never got out of India. So now we've got 2 negatives. We've got -3, and we've got looks like -2.5. So you know, roughly -3 into -2.5 is going to give you approximately, looks like 7.5. So these are all of the wonder things that I reckon would be great for children to start to learn about. We've got a beautiful symmetry in number and magnitude that has simply not emerged. So what we do with multiplication, Descartes also said on that same diagram, he then also gave an explanation on how you can work out division with that same initial diagram. To save time, I've simply said now the ratio that we look at is the ratio of b to 1. So there's our vector that's going from b to 1, and then there's our multiplicand. Sorry, we've got to drag that. So we're going to change the dividend, and as you see, as we change the dividend, I've got a negative dividend, and I've got a positive divisor, I've got a negative quotient. Whoa, look at that. How cool is that? I bring things over. Now I'm going to have a negative multiplicand, and we'll see that it's switched around. It's a little bit hard. I usually bring a mouse, but I left that at home in Australia. Sorry, I've got to make the, sorry, I'm dragging the wrong one. I've got to change A and B, and you see we've got a positive quotient C, as you'd expect with similar triangles. So anyway, these things haven't yet really emerged. So I now jump back to the slideshow presentation. So then that's just simply the pictures frozen in the PowerPoint. I've got the addresses there as well. So if you click those URLs, you'll get to those GeoGebra applets, and you'll be able to start to share them with school teachers. So there's the applet for the division as well. So as you can see, as the divisor B is to the fixed unit 1, the dividend A is to the quotient C. So this is just following on from that simple song. The vision you see is lots of fun. Do 2 A's, B made 1. The children will know how to play the game. Okay, so here's an article that I had published, a new model of multiplication via Euclid. Now, what I've had my own secret fun doing, and I've kind of kept this to myself, is I've actually morphed together the Euclidean plane onto the Cartesian plane. And I've started to put numbers onto Euclidean diagrams, and I've started to have negative line segments as well as positive ones, and all of the mathematics that comes out of it is pure Indian, balanced, symmetrical. So it's really cool. This was the first thing that I developed, and this man is responsible. There was a video on YouTube that I saw a while back. I think it was on the history of Indian maths held by the IIT. I think he spoke at it. One of the professors asked the question about why are there no numbers in Euclid's elements, and he said that they only ever found the number 2, and that was like a trapezoid is the sum of 2 angles, 2 triangles drawn from the diagonal. So anyway, the reason why that numbers have been separate from geometry is because of Aristotle, who said geometry cannot be proven with arithmetic. So if you started to try and put numbers onto any Greek mathematics, which is essentially Euclid, you were sent to the sin bin, because Euclidean proofs were never meant to have any numbers, because they're meant to be universal proofs and not case-specific proofs relevant to just one instantiation of a set of numbers. So that's in answer to that professor's question, that why are there never any numbers in Euclid? It was actually a law. It was banned. You just had to use deductive proof. So, just going back to here, I've had so much fun in my own little head creating fun things that people have never seen before. So here, for example, we see multiplication on the real number system generated by a circle. So I've got a fixed unit 1, which is from 0 to 1, and I've got the multiplicand A here, and as you see I increase the multiplicand, the intersection of the circle on the y-axis generates the product. If I change the multiplier, you can see that the circle produces the product for me. So I've shared this diagram with professors of geometry at Cambridge and Oxford, and nobody says they've ever seen anything like that. And that's kind of like the only fun thing I've really done. I've really been stuck in the history of why does mathematics seem logical. But that article was all about the similarity of triangles and proportion, that says that as soon as you start to put geometry on top of Cartesian planes, you get really new interesting lessons that start to emerge that we're not using in the classroom. And these lessons can be fun because they're visual, and they also translate. If you go to that article, I've got the link where you can download the article. So if you click on that, you go straight to the PDF and it will download on your computer. So, how are we doing for time? Okay, 3:30. I've got about another half hour. Okay, so anyway, Aristotle set up the situation where it really put us on the wrong tram for a very long time. Now, people started to, Ludolf van Seulen put numbers on Euclidean diagrams, and also the famous Fibonacci did put numbers on Euclidean diagrams, but he didn't do it in Liber Baci. He did it in Practica Geometrae. So if you look at the other book, the unknown, almost unknown book of practical geometry that Leonardo Pisano wrote, you'll see numbers on Euclidean diagrams. And it's really cool. And almost nobody teaches from it, which is a real shame. And that came out in the year 1220. So imagine if that became as popular as Liber Baci, at least we would have had more fun in the classroom today. Okay, so discussion on Brahmagupta's laws, and by discussion I mean more monologue. So we've got positive 1 by positive 2 equals positive 4 by positive 8. And even though the numbers are different, both numerators are smaller than their denominators. So if one side has a smaller number on the top and the other side has a larger number on the top, even if we use the same numbers as before, that is now an inequality because that number is less than that number and that number is greater than that number. And that's kind of almost common sense. But look at the following equation. Positive 1 by positive 2 equals negative 4 by negative 8. That is a true equation. But if we accept that that is an equation, just as positive 1 is less than positive 2, we must accept that negative 4 is less than negative 8. Ba-bum-bum. And that is completely different to the way that mathematics has evolved in the West, because they have been saying for centuries that any number to the left of 0, for some reason, I'll explain, is less than any number to the right of 0. And Brahmagupta defines 0 as the sum of two equal and opposite numbers. Brahmagupta had a lovely equal symmetric view of the world. There are no negative numbers in the heavens. There's only magnitudes. And there's gravitational forces in equal and opposite directions. So Brahmagupta's laws say, uh-oh, the West has got a problem with its inequality logic. And it's never made any sense to me. And again, my journey through mathematics has been whenever things haven't made sense to me, I thought I was stupid in the first instance, but then I wanted to find out why in the second instance. So the British system is greater than negative 8, which is illogical given positives and negatives are equal and opposite. Brahmagupta's laws of integer ordering are intuitive, logical and correct. So, the same number of positives and negatives sum to 0 as they're equal and opposite. Therefore, today's integer inequality laws, based on Greek foundations, 1,000 years older than India's, are out of date and suboptimal. They're bad. So, seeing is believing. Look, which numbers are greater? Here we've got 1, 2, 3, 4. We've got 5 positives, and then we've got 7 negatives. So which number is greater? The kids are going to say this one, and the kids are going to be right. So, all we do is we work out which one is greater by cancelling out the zeros. And so there's the truth of integer inequalities. 5 positives are overpowered by 7 negatives. Why? Because after they meet and they cancel out the zeros, we've got 2 negatives remaining. So that's why I'm saying we really need to start rebuilding the elementary mathematics pedagogies from our correct understanding of India's 0. And again, this is just for your eyes, so I'm not going to read this one. But you can just start to say, well, of course, it makes sense now. All of these statements are now true statements. But they're not what any maths teacher in the West would give you a tick for, even though this is the truth. Okay, so what lies do we know? To multiply a by integral b is to add a to itself b times. You'll find this shopkeeper's definition that makes no sense in hundreds of dictionaries around the world. And nobody knows that it was invented by a shopkeeper. They're all saying it's Euclid's, but no, it's a shopkeeper. And what happened is Henry Billingsley became the Lord Mayor of London. And then he got knighted. And so he became Sir Henry Billingsley, first English translator of Euclid. He got all of this prestige as if he was knighted like Sir Isaac Newton. But he was a shopkeeper and he's a politician. He wasn't knighted for mathematics. He was knighted for being a politician. So, in Book 7, Euclid defines multiplication as when that which is multiplied is added to itself as many times as there are units in the other. That book is the #1 teacher resource on how to understand multiplication. And when it starts off with saying multiplication is repeated addition, it's not going to get to the truth. Because that's the shopkeeper and that's not Euclid. Okay, now, here's my little 7-year-old head. What does 1 into 1 equal? Well, the teacher says it's 1. But what does the definition say 1 into 1 equals? Well, 1 into 1 equals 1 added to itself 1 time. And I learnt the doubles. I was really good at addition, and I was really good at the doubles. So 1 added to itself 1 time was 2. But my teacher says that 1 into 1 equals 1. Another brain explosion. Not just in my head, but in children's heads for centuries. But whoever listens to children saying they don't understand, the children are said to be stupid because they don't understand. Well, I'm saying that it's the mathematics which is stupid in the classroom. Because the mathematics is only ever truth, but we've only ever had really bad explanations. Okay, so the above definition is from Henry Billingsley, a London shopkeeper who changed Euclid's definition upon translation into English. Euclid, the actual definition of Euclid is Euclid gave us AB, and I'm using modern vernacular, AB equals A placed together B times. So that if you've got 2 into 3, that means that you're going to place 2 as many times as 3 units in 3, so you're going to place 2 3 times. Place 2 once, place it again, and you've got 6. So the Euclidean explanation is perfectly sensible. That's still an additive instantiation. It's still much more of a proportional idea in Euclid, but that's a good way to introduce it to the classroom. And if you click into this link here, you'll see me write a monograph about this, basically. And that's my experience I had in class 2, when I said that 2 added to itself 3 times was 8, and India's 0 was missing. That became a peer-reviewed published paper, The Lost Logic of Elementary Mathematics. And if you click the link, then you'll be able to download that paper as well. And I've got a whole bunch of really cool references in that. And basically the scientific method has never been applied to mathematics. Why? Because mathematics is based on definitions. We start with definitions, and then we've got a problem, and then we use the definitions to work through a proposition to generate a proof. Now I kept on asking professors, who has proven Euclid's definition to be true? And they say, we don't prove definitions to be true, that's where we start. So we had this really peculiar chicken and egg situation. No one ever fixed the definition of multiplication. Even though it was crashingly obvious it was wrong, it was Euclid, and we're not going to fix it because you don't change Euclid. And so all of the laws and rules that then emerged in the pedagogies, those laws and rules weren't laws and rules of mathematics. The operating system was badly written, and so the laws and rules we teach children are bug fixes. That's when we make a law, we make a rule because our understanding is wrong, and we've got to say, forget the explanation, follow the formula, obey the rule, and then the numbers work. And that's why children don't like mathematics. We want simple explanations that work. And for centuries we've been told, sit down, be quiet, listen, this is the law, this is the rule, memorize it, and then you'll understand it. And if you don't understand it, you're stupid, go do cooking or something else, you're not ready for mathematics. That's my anger coming through. I've had 50 years of it. Okay, I'm better now. Returning India's 0 reveals beautiful patterns. So this is the correct way we can start to depict multiplication. A into positive b equals 0 plus a 4 times. And we've got this beautiful symmetry starting to appear, boing, and then boing. So every time we go down this way, we're dividing by a, divided by a, divided by a, divided by a, by a, by a, by a. And every time we go up this way, it's into a, 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 into a. We've got all these beautiful symmetries that really haven't appeared, as far as I can tell, in any textbook for children. Because the definition never had 0 in the definition of multiplication. So integral multiplication involves either repeated addition or repeated subtraction of the multiplicand from 0, depending on the sign of the multiplier. We've never had people talking about negative multipliers. They just haven't even understood 0. What hope did they ever have to understand the meaning of a negative multiplier, meaning to subtract the multiplicand from 0, because 0 is not a number. How can you take anything away from 0? Well, as we saw, we just start to add 0 to 0. Okay, so what I have talked about is the Billingsley virus of 1570. I've actually called it a virus. I've called it BV 1570 because that's when a logic virus was unleashed in the West, courtesy of a shopkeeper. And that virus has not only infected subsequent mathematics books, people have gone back and they have been changing ancient textbooks So the ancient definitions written in Hebrew and Latin were changed in translation to English so they matched the shopkeeper's explanation. I've caught many scholars out. They say they've translated from Hebrew, and I know it's not correct. And they give the shopkeeper's translation of Euclid's multiplication out of the Hebrew. I go off to 3 professors of mathematics in Israel. I double check the Hebrew. Nah, that scholar, no, you're a naughty boy. In the Latin as well. Because I only saw my eyes. I knew what was true. I thought I was stupid, and I failed mathematics at one time and repeated a year of school. But later on, at my first job interview, I was given a psychological test for my job. They said I was in the top 1% of verbal logic. I was in the top 1% of mechanical reasoning. So how can a little boy in the top 1% of the population fail mathematics? I thought I was stupid for much of my life without knowing that actually I was a very bright little boy, made to feel stupid. Now there are millions of children around the world far cleverer than I who are also feeling stupid because they're not understanding the lessons. So, if you click the link, you'll learn more about the Billingsley virus in German, Latin, Hebrew. In fact, my research is covered. I'll quickly try and go through them. I've done my research through people who are experts in the native language. I speak English, but I've got about 17,000 connections on LinkedIn. So whenever I need a language converted, I'll get a professor of mathematics, like, you know, if it's Greek or if it's Latin or whatever, I'll have a professor of maths do my translations. So I've done my study in Latin, ancient Greek, Sanskrit, Arabic, Hebrew, French, German, Italian, Russian, Dutch, Czech, Spanish, Czech, Mandarin, Japanese, Korean, and probably a few others. I've probably overanalyzed this through about 20 different languages through the course of my study on primary school mathematics. That's why it's taken me basically decades to get to this point. Because if I'm saying that the world's mathematics is structurally flawed, I really need to get that evidence together. Or else people just say I'm another crank, another heretic, another guy who says, oh, I know how to square the circle, when we know it's impossible. Hoda the puppy squares it, but the Shilva Sutra wrote, which is definitely possible. Okay, so putting 0 back into the definition of multiplication brings back the symmetry. And how weird is this? When explaining a to the power of 3, Sir Isaac Newton used the Latin word bis, meaning twice. So a to the power of 3 is a twice multiplied into itself, according to Isaac Newton, in the Latin. Yet, because of Henry Billingsley's mistranslation of Euclid's definition of multiplication, upon translating from Newton's Latin into English, the translator changed Newton's explanation of exponentiation. So, Sir Isaac Newton, one of the greatest geniuses, he knows about basic arithmetic, and Isaac Newton also wrote that if we deem this line segment to be positive, we can also deem this line segment to be negative. So Isaac Newton knew about the concept of equal and opposite. Why? Because he was all about gravitational forces. What did he have? He had his third law: for every action there's an equal and opposite reaction. So somehow he saw the truth, probably because he was an astronomer, like the Indians. So he had correct explanations of arithmetic, and they were changed to match the shopkeeper. So then people started to read Isaac Newton's explanations of arithmetic, and it was the shopkeeper's explanation, and they kept on with it. Because not only Euclid said this sort of stuff, but so did Isaac Newton. Of incorrect translations. Okay, so I provide all of the original Latin and so on in my research. So, to cube, the result of multiplying a number, quantity, or expression by itself 3 times. In dictionaries, if a to the power of 3 is a into itself 3 times, we get the sequence a into a into a into a, because we've got 3 intos, into. So if 2 to the power of 3 is 2 into itself 3 times, we get the sequence 2 into 2 into 2 into 2, which is 16. And we know 2 to the power of 3 is 8. So imagine me as a student saying, oh yeah, from what you tell me about 2 to the power of 3, yeah, I get 16. No, it's 8. And I'm straight back to my confusion from grade 2. Now, so 2 to the power of 3 doesn't equal 16, even though that's what the dictionary definition tells us to do. Now, teachers will often do workarounds, and they'll give alternative explanations, but more often than not, they're suboptimal explanations. Okay, so just as India's 0 went missing from the definition of multiplication, we now know that 1 went missing from the definition of exponentiation. Both identity elements went missing, 0 and 1. So now, we return the identity element 1 into exponentiation. So here is now the truth. Look at this beautiful pattern. A to the power of 4 is 1 into A 4 times. A to the power of 3 is 1 into A 3 times. Now, one of the things that's always confused me, and if it confuses me, I'm in the top 1% of the world for verbal logic and mechanical reasoning. If it confuses me, it's probably going to be wrong. Why does 12, this is not in here, but why is 12 to the power of 0, 1? The definition that we saw a couple of slides ago, anyway, 12 to the power of 0 should be 12 into itself 0 times. Okay, now if you've got 12, and if you're not multiplying it at all, it should stay 12. But it's equal to 1. Now sometimes maths teachers will say, professors will say, well, the exponent really counts how many times the base appears as a factor. So 2 to the power of 2, the little 2 at the top says that the base appears twice as a factor. So 2 to the power of 2 equals 2 into 2. And so the definition is wrong, but our teacher can still help us get around that. But 12 to the power of 0, that means that there's a 0 exponent, which means that 12 appears in the base no times at all, so the answer should be 0. So either the definition of 12 to the power of 0 equals 12, or the teacher's explanation would have you believe that it equals 0. That's because the definition's wrong. And it has been for centuries. So that's exactly the pattern where everything starts from 1. And integral exponentiation involves either repeated multiplication or repeated division of the base, which is A, from 1, depending on the sign of the exponent. So, A to the power of positive B, correctly defined now after a few centuries, is 1 into A B times. 2 to the power of positive 3 is now correctly explained as 1 into 2 3 times, which is 1 into 2 into 2 into 2, which gives you the 8. Yay! If I got that at school, I would have been a happier boy. And similarly, A to the power of negative B becomes 1 by A B times. And so 2 to the power of negative 2 is 1 by 2 3 times. So 2 to the power of, sorry, that should be a 3 there. That should be 2. I'll have to fix that slide. In fact, I might do it now. So that's 2 to the power of negative 3. Okay. So 2 to the power of negative 3 equals 1 by 2 3 times. So 2 to the power of negative 3 is 1 by 2 by 2 by 2, which is why you get 1 over 1 by 8, or 1/8. So all of the index laws that you were taught to memorize pretty much now have become a consequence of the definition. So if we've got 12 to the power of 0, that equals 1 into 12 0 times. So it's going to stay 1. So anytime we've got an exponent of 0, it's telling us we're not going to divide by the base and we're not going to multiply by the base. It's just going to stay the number 1. So if you have the correct definition of exponentiation, it's obvious from the definition, anytime you've got an integral exponentiation of the exponent is 0, the answer's got to be 1, you're not doing anything to 1. And that gets away all of the confusion about the index laws, and in particular why 12 to the power of 0 equals 1. And I've got a really good fun link for you to enjoy later on, cube confusion. And this is where I said that everyone's entitled to their own opinion, but not to their own facts, click on that link and you're guaranteed to have a laugh. Because all of these definitions are in mathematics dictionaries. And the mathematics dictionaries are informing the public on our love, our passion of mathematics. And what people are doing to our mathematics that we love is destroying it with nonsense courtesy of 16th century England and what followed. So let's look at the simple symmetries of quantity. We've got on the left of 0 on the conventional number line, we've got counts or measures of negative units. And on the right of 0, we've simply got counts or measures of positive units. And I'm just starting to move along because I'm realizing I'm running out of time a bit. So it's been said God created the universe from nothing, from shunya, from 0. So imagine now we're an astronomer again. Forget the mathematics, that's just a tool for our understanding of the universe. So imagine we've got planet negatron, and the gravity on planet negatron is a force pulling us towards the left. But in our universe, from the Big Bang of symmetry, we've also got planet positron, and the gravitational force from planet positron is pulling us towards the right. Now, if in that moment in time, we were completely in the middle between both planets of equal mass, we would have 0. 0 is the sum of those two vector forces. So wherever opposing quantities or forces are equal, you will find 0. And this means that Brahmagupta's logic is entirely consistent with how the universe works. But all of the mathematics, which is meant to explain the universe, all it's doing is saying that all the numbers which represent quantities, they're less than those ones. That's discrimination. That's just like wrong. And on that aspect of discrimination, I'm going to call it, I'm going to say that there's been an amount of racism in the evolution of mathematics. The Europeans thought, what would we ever get from the Indians and the Chinese when they had Aristotle, they had Plato, they had Euclid, they had the greatest intellectuals, but the Greeks had lousy arithmetic, as you know, they didn't have numbers, they used letters very often, and the Greek mathematics was based on geometry in which negative numbers and 0 and 1 weren't numbers. And yet we go back to the mathematics built from the understanding of the universe. That's how Brahmagupta got his laws. He got his laws because they were consistent from astronomy. So I just thought it'd be nice to put in an astronomical metaphor back in here to show the consistency from Brahmagupta to modern day physics. Okay, so the Big Bang is silent. When I actually went bang in the classroom to the little children, they got an almighty shock. So it's as if 0 was split, creating infinite real number lines from 0. So there's the number line with 0 in the middle with a little smiley face. You'll see this when you get the PowerPoint presentation. And continuing the discussion on Brahmagupta, I've got a few students looking in, hello there. China had positives and negatives in the 2nd century BC. Yet their first maths text with India's 0, or at least this is the oldest extant book that we've got, came in 1247 in the mathematical treatise in 9 sections. So China used positive and negatives in their mathematics for 1,400 years approximately without any concept of the number 0. So the Chinese did not define negatives as less than 0. Their positives and negatives were simply equal and opposite, consistent with science and the philosophy of yin and yang. And the Chinese mathematics is largely consistent, although inferior, to what India subsequently developed. Because the Chinese effectively had an empty position on their counting boards, and people have always said that, yeah, well, that's basically 0. Yeah, okay, well, the Indians, they didn't have counting boards, they did it in the dust, so they needed to get their finger and go and make it 0 to split out the numbers to get them in the right column. But no, the Chinese never, and I looked at the book by Crossley and the others on the 9 chapters and so on, the Chinese never ever would have thought of adding an empty place to an empty place to solve a mathematical problem. But that's what we see we can do with Brahmagupta. We can add 0 to 0 because we know how to define 0, and by adding 0 to 0 we can solve integer arithmetic. Chinese never had anything like that. Yes, they had Gaussian elimination, but they never had any simple arithmetic that emerged to be as powerful as what the world never got to know. So, is 0 defined as a number subtracted from itself? I'm wrapping up. No, Brahmagupta's additional law 4 says 0 is the sum of equal positive and negative quantities. 0 is defined by addition, negative n plus positive n, not subtraction. And why is it defined that way? It's defined for use with the Indian laws of positives, negatives and 0. So this is a self-contained system. Why did he define it that way? Because that was the system of his algebra that he explained in chapter 18, verse 30 to 35. Our lessons on inequalities correct? Is negative 4 really greater than negative 4? No. Subtraction law says that if a larger negative is subtracted from a smaller negative, the sign of the difference is reversed and negative becomes positive. So we prove that negative 4 is greater than negative 7 false by contradiction. Assume negative 4 is greater than negative 7 true. We subtract larger from smaller in the form of negative 7 minus negative 4, and the difference is negative 3. As the sign of the difference is not reversed, we cannot assume negative 4 is greater than negative 7. Thus, negative 4 is less than negative 7, as seems obvious. A debt of 400 rupees is less than a debt of 700 rupees. Don't let anyone tell you any different, because they're going to steal your money. So Brahmagupta's subtraction law 3 also holds for greater positives subtracted from smaller positive. Why? Because positive 4 minus positive 7 equals negative 3, and the sign is reversed as subtraction law 3 states. So are negative numbers less than 0? No. Numbers represent counts or measures of quantities, even abstract units. The Big Bang created matter and antimatter, equal in magnitude. Electrons have negative charge and positrons have positive charge. And as you know, Dirac won a Nobel Prize for predicting the existence of positrons based on mathematics. Now, he probably didn't have Indian mathematics, but maybe if he did, that would have been solved before Dirac came out with his theory. Now, when antimatter and matter meet, they annihilate each other, producing energy. So they come together, one positively charged, one negatively charged, they meet, they release energy, poof, and then you've got 0 again. It is said God made integers. Those integers are consistent with physics. And in black writing there, in a really dark grey, I actually acknowledge baryon asymmetry. And if we ever unlock the secrets of baryon asymmetry or the matter-antimatter puzzle, we'll directly be talking to God. So, something which I like to say, which is a bit of a joke, if God made the integers, when it comes to fixing the foundations of elementary mathematics, the devil is in the detail. Okay, are negative numbers less than 0? No! The Chinese used positives and negatives for 1,400 years with no need to move away from the idea they are equal and opposite. That's what their rod numeral arithmetic was all about. The idea negative numbers are less than 0 emerged in 1685 via Englishman John Wallace. If after marching east 5 yards, 1, 2, 3, 4, 5, a man was forced back 8 yards. Oh no, bad! 1, 2, 3, 4, 5, 6, 7, 8. Wallace said in total, I'd advanced 3 yards less than nothing. Okay, well that's logical, but any Chinese or Indian would have said that I had simply retreated 3 yards. I hadn't advanced 3 less than nothing, I just retreated. We've got these equal words in language that match up with the equal numbers, negatives and positives. So it's basically a grammatical disaster. Today we don't talk about driving to work east and then going home negative east. We have west and east, equal and opposite. We've got north and south, equal and opposite. Even though if you do put negative geometric coordinates into your sat-nav, they still work, which is really cool to play with. Okay, so here's the original diagram. So, in the metaphor, the marching man started at A, advanced 5, and then he was forced to back 8, and then John Wallace said that the man had advanced 3 yards less than nothing, because he started there and finished there. but any sensible person would have said, okay, if I started there, I retreated 3 yards. So what a disastrous, bogglingly confusing metaphor, which led to the idea that numbers on this side are less than nothing because of a silly marching metaphor. Now, at the time that John Wallace created this metaphor, the English were at war with the Dutch. And so advancing towards the enemy was that way. Now, if history had changed and the English had been at war with the Irish, we'd have the positive numbers on the left and we'd have negative numbers on the right. So this is meant to be science? This is garbage. And yet, oh, what a wonderful explanation of negative numbers. No. Remember, I'm failing the entire evolution of mathematics at elementary level. Okay, so maths is about relationships between quantities, and the quantities don't have to be the same kind. Numbers are only ever counts or measures of quantities, even if the quantity is a unit. Now, too many mathematicians say mathematics is the science of patterns. Well, I've got plenty of patterns I can show you that lead to paradoxes and contradictions. You need to just get back into the universe, which is all about quantity. And we're looking at positive numbers and negative numbers as representing different opposing forms of quantity. Okay, so for example, if people drive a car, maths looks at the relationships between quantities of distance and time to get average speed. There's also the quantity of fuel and the distance, which generates the maths called the fuel consumption. So every time you look at the real world application of mathematics, you don't find negative quantities. In science, you don't have, in the universe, you don't have quantities less than nothing. And yes, we've still got barrier and asymmetry, but there's probably a multiverse model that solves all that. So, facts you may not know. In 2010, the states of Tamil Nadu and Himachal Pradesh were selected by the central government to participate in a global maths comparison. In mathematics, considered India's strong point, the 2 states finished second and third to last, beating only Kyrgyzstan. So this is not your fault. This is what happens when you have an Indian mathematics which is intuitively obvious and correct and consistent with the universe, and somebody takes away Indian mathematics from you and gives you garbage nonsense that's based from colonial England, that was exported right throughout the British Empire. Why? Because the English had the printing press, they published all these English language mathematics books, and they exported their garbage, including the shopkeeper's definition of multiplication, to all of their settlements and colonies. So BV 1570 came to infect the entire world and unnoticed. So, India has the wrong maths. You're doing bad. Maybe that's just fate telling you you've got the wrong mathematics. I mean, look at the mathematics results you have in PISA and TIMSS. Okay, give up the Greek-English garbage, revert back to going back to the roots of Brahmagupta in the elementary schools, and I guarantee you, in 10, 20 years' time, you're not going to be second last. You'll go way up in the rankings. And it'll be the cheapest thing the government can do to its education system, because mathematics becomes the platform upon all the STEM subjects, science, technology, engineering and medicine. I call it medicine because mathematics is the platform for them all. Okay, so you've got Greek-based pedagogies developed in 16th century England. Does India have the courage to teach its own logically superior mathematics? Yes or no? I'm saying India has the right people because you guys love mathematics. Now, I'm hoping that India, if it loves mathematics now, will really love to get mathematics that's Indian mathematics. That's consistent, logical, and gets rid of the colonial nonsense that was perpetrated by the East India Company. And, oh, history is a horrible thing, but at least now we know. Okay, so 0, the equilibrium point, where opposing quantities are equal, is the starting point of relationships between quantities. Numbers count or measure quantities, and the study of relations between quantities is called mathematical science. Therefore, 0, negatives and positives must be the starting point of mathematical science. Thank you very much.
ensure a lot of discussions on that. I think considering the time, and Indian time in particular now, and all is ready to go, maybe to leave, and this is an institution which you have to look around. What's the time now? 10 minutes past?
10 minutes for 8 minutes for
Right, to be precise, isn't that? Maybe 7.5 minutes, something like that. I would rather presume that maybe 3 to 4 questions may be asked, not more than that. But see to that, there's an institution and would like to talk to our about how long we will keep it open and sure about it. So, I think
Yes, I'm very happy for any questions. What I'll also just say is that please give me some feedback at jonathancrabtree.com/feedback. There's a little form there. You can ask your questions, and you can also give me feedback on what I need to explain better.
nowadays we have ways to do things instead of projecting any other yourself on yourself. Yes. So I say, to my perception, there's a lot of things that need to be discussed and talked about, and I think there is a marvelous one that we will say later. But again, I leave it to Robert to conduct this and for the vote of thanks also. You ask questions also. You also.
Is the vote divide 0 divided by 0?
Is still the divisor. So you've got to go to Bhaskaracharyya to get back to the concept of infinity or being indeterminate. The simple contradiction, imagine you've got the number 1 on the numerator, you've got your vinculum, and then you've got 0.5 on the bottom. So you've got 1 by a half equals 2. So what we're going to do is we're going to look at the pattern here. So 1 by 0.5 or a half equals 2. So 1 by 0.25 or 1 by a quarter equals 4. So we're going to get a very simple pattern. As the denominator gets less, the number that fraction represents gets larger and larger. 1 by 0.1 or 1 by 1/10 equals 10. Now, what we do is we pursue that. We get smaller and smaller and smaller and smaller. We get 1 by 1 millionth equals 1 million. Now, you keep going and then you get India's lovely numbers of 0. 1 by 0 is, like by the 12th century, considered to be infinite. So 1 over the smallest number equals the largest number. So if we say Bhaskaracharyya had that sort of concept. Now, if you say that 1 by 0 is infinite, and if you say that -1 is less than 0, then the pattern says 1 by -1 must be greater than infinity. Okay? That's a logical conclusion. If you say -1 really is less than 0, then 1 by -1 is greater than infinity, which is not, it's -1. So there's all sorts of very simple ratio and proportion concepts which prove that negative numbers are merely equal and opposite. Now, I've got to admit, I'm not a real guru on Aryabhata or Bhaskaracharyya. I've looked at the English translations of Brahmagupta and all of the others, but my focus has been on elementary mathematics. I haven't been looking at the astronomy of these people. I've been trying to decipher what they mean by their laws. Now, in the West, there are many, many school books which are misrepresenting Indian mathematics. So in Australia, there are 3 textbooks for school teachers. They all quote Brahmagupta. And you think, well, that's really good. No, it's a disaster. Because what they do is they say, Brahmagupta said, debt into debt is positive, a fortune. Right? Now, the Indians never used a financial analysis to explore astronomy. I've looked at all of the laws of sign of the Indian astronomers, and they only ever use the word negative, not debt. Now, I then asked people, okay, who here owes money on a home? Who here has got money on a credit card they owe? Okay, if you want to get rich, multiply your mortgage debt, multiply that by your credit card debt, and you'll get a fortune. It's absolutely nonsense. what Brahmagupta gets us to understand is that negative into negative simply means a negative subtracted from zero. So if you had a debt that you had to pay every month of, say, 1 lakh rupees every month, now if I came along and said, I'm going to take away your debt for the next 10 months, my subtracting your debt or subtracting your negative is a fortune to you. So you can have a financial metaphor, but the people who keep on writing that the laws of Brahmagupta are a debt into a debt is a fortune, and a debt, I mean, it's just complete nonsense. And it goes into the maths books, and then the children see, how am I multiplying two debts to get a fortune? It's nonsense. It's, again, misrepresenting Indian mathematics. And I've taken people to task, like George Zifra. In his Universal History of Computing, he's even got debt by debt equals a debt. He's even got it wrong. But in the original French, he had it right. So George Ifra, in his big fat book, The Universal History of Computing, or Numbers, he had it correct in the French, and when they translated the French edition of his book into the English, another incorrect translation creeps in. So it's just, we think that mathematics is this polished jewel, which has been incrementally passed on with great care. Take it exactly as it is. Thank you very much. I will treasure it. I will polish it. I will add only good logic to it. No, it's been nothing like that. It's been disaster after disaster after disaster. And one thing is, if you look at the algebra of Al-Khwarizmi, I try and get inside people's heads. Like, I try and psychoanalyze what was their life like. And the beautiful thing about me is I know no mathematics. So I'm not taking a modern understanding of mathematics and applying it to the ancients. Like people say that look at the books of Euclid, it's all algebra. No, it never was algebra. But we interpret it now as algebra because we can't understand their original mindset. Now, I got back into the mind of Al-Khwarizmi and his algebra. And what was he on about? Balancing and restoration. Now, the Arabs were great traders. They went into the marketplace, and a lot of Al-Khwarizmi's books were about inheritances and money and financial transactions. Why were the Arabs so much into money, not so much astronomy? It's because Muhammad was a trader. So he kind of set the precedent, money and mathematics is good. So Al-Khwarizmi's got this balance and metaphor. And if you look at his quadratic equations, he'll have ax squared plus bx equals c. Okay, and so you look at his 6 forms of his algebra, okay? Nowhere will you ever find ax plus bx equals negative c. Nah, because you've got to balance positives. And guess what? You'll never find these algebraic terms equaling 0 because you've got all ax squared plus bx plus c equals 0, and this is 0. They can never balance. But we know 800 years later, Napier solved quadratic equations by factorising them and making them equal 0. And then you got the roots of the quadratic curves, but it took another 800 years to get the right algebra from the Arabs by having numbers balancing against 0. So there was a lot of damage done to Indian mathematics on its transmission through the Arabs in medieval Europe, that all the good stuff was basically lost. And now I'm finding, whoa, this is so much fun to go back and apply India's laws and logic to all of the stuff people have done in the past, and then suddenly things become so much clearer.